across the rooftops of India's cities, and you'll see a rapid infrastructure shift underway. Through government programs like PM Surya Ghar, hundreds of thousands of residential rooftops are being converted into active power centers. These localized installations are a crucial piece of a specific national target, reaching 500 gigawatts of non-fossil fuel electricity capacity by 2030. Hitting that number using only traditional utility-scale solar farms comes with a severe physical constraint. A ground-mounted facility requires up to 4.2 acres of flat land for every single megawatt of power it generates. In a densely populated nation where nearly 60% of the land is dedicated to agriculture, fencing off vast tracts of flat terrain for solar arrays puts clean energy generation directly in conflict with food security. Relying solely on these solar parks to hit mid-century climate targets would consume millions of hectares of arable land, potentially crippling the nation's agricultural capacity to protect its climate. Building mounted solar offers a physical workaround. By attaching panels directly to existing urban structures, a city can generate gigawatts of power without acquiring a single new acre of land. This side-by-side diagram illustrates the mechanical advantage. When electricity travels vast distances from remote plants, the grid loses 5 to 10% of power through the wires. Rooftop systems generate electricity at the point of consumption, effectively eliminating line losses. When paired with battery storage, these systems become autonomous. During extreme weather events or widespread blackouts, hospitals, fire stations, and homes can keep their critical infrastructure running independent of the broader grid. From the outside, this looks like the ideal clean energy solution, power generated and consumed locally with zero emissions. But the physical hardware on those roofs hides a structural weakness. To achieve this level of local independence, the world has made itself dependent on a single, hyper-centralized and fragile global supply chain. While a solar panel might sit on an Indian rooftop, its origin story usually begins thousands of miles away. Over the past decade, solar manufacturing has migrated out of the US and Europe, consolidating heavily inside China. This visualization breaks down the global supply chain. For the final stage, solar cell assembly, Chinese manufacturing controls 85% of the market. But adjusting to focus on the midstream choke point, highly refined silicon ingots and wafers, that market control spikes to 97%. Securing that level of market dominance requires incredible amounts of energy. Refining raw metallurgical quartz into pure polysilicon demands continuous, intense thermal processing. To meet that energy demand, the majority of the world's polysilicon is processed in regions relying heavily on coal-fired power, such as China's Xinjiang province. A solar panel operates for decades with zero emissions, but the heavy carbon footprint required to manufacture its core components upstream creates a glaring contradiction. To counter this bottleneck, major economies are fighting back. India deployed a multi-billion-dollar policy known as the Production-Linked Incentive to subsidize domestic solar manufacturing. On paper, the policy worked. Indian solar module capacity surged from just 8 gigawatts in 2021 to over 170 gigawatts by 2026, drastically cutting the country's reliance on finished imports. However, scaling the upstream production of raw ingots and wafers requires specialized technical expertise and heavy capital investment. As a result, many Indian factories are simply importing Chinese-made wafers and performing the final assembly locally. And whether a panel is assembled in Delhi or Beijing, it eventually reaches the end of its lifespan. By 2050, the world is expected to face a wave of aging solar waste, totaling up to 160 million tons. Right now, the recycling rate for decommissioned panels in the United States is below 10%. While the glass and aluminum are easy to melt down, trace elements like silver are present in such small quantities that extracting them is barely profitable. Without a way to recover these materials, panels end up in landfills, risking leaking toxins into the surrounding soil. This leaves us with a stark reality. India is paying to assemble carbon-heavy components that eventually become unrecovered toxic landfill waste. Walking away from distributed solar isn't an option. The localized benefits are critical for grid stability. Instead, the physical supply chain itself must be re-engineered. The first step is closing the upstream gap. National reshoring policies like India's PLI need to evolve. redirecting future funding away from module assembly and toward the difficult processing of raw polysilicon. The second step is leapfrogging silicon entirely. The industry is aggressively investing in the commercialization of perovskite tandem cells, a next-generation technology that layers a highly efficient synthetic crystal directly over standard solar materials. Perovskites require raw materials like iodine and organic salts, which are abundant globally. More importantly, they can be processed at very low temperatures, neutralizing the thermal energy advantage currently held by Chinese manufacturers. Finally, the life cycle loop must be closed. Regulators need to implement extended producer responsibility frameworks, mandating that manufacturers standardize the recovery of bulk materials like glass, aluminum, and copper at the end of a panel's life. The energy savings here are substantial. Recovering and recycling the aluminum from an old panel uses 95% less energy than mining and processing virgin bauxite from the earth. Mastering the industrial life cycle, from the first gram of silicon to the final stage of retirement, is the only way to achieve true energy sovereignty.